All right, today these slides say we are in session 7. We are actually in session 6, so I will get that fixed. But we're going to talk about modeling methodology. What are all the steps that you need to go through to actually build a robust and a performant model? We've already started to understand what logistic regression is, what linear regression is, decision trees and random forests and unsupervised learning algorithms and clustering. And now we're here with great. How do we take our data and ensure that when we do apply these algorithms and after we do select the proper algorithms, that we're defining a methodology that enables us to accomplish our ultimate goal? And our ultimate goal is to build models that generalize to unseen data, models that are generalizable to real world data when we implement them. So that's the goal of modeling methodology, is to set us up to be successful. So what is a machine learning model? From Databricks is a platform that can help you manage your data at an enterprise level. And it's a platform that brings together data and machine learning into one platform so that you can actually run experimentation with your machine learning models and your data all on one platform. And they have a definition here for machine learning model, which is a program that can find patterns or make decisions from previously unseen data. And a machine learning model can perform these tasks by being trained with a large set of data. And during that process, it's optimized to find certain patterns or outputs from those data sets. So it's optimized by those algorithms that we've talked about in the specific type of algorithm that it's implementing. So if that's a model that's being optimized to perform based on some algorithm, perform based on this data that it's seeing, how can we make sure that it's seeing data and it's training on data in a way that generalizes, that when we take that same model and apply it to a different data set, it's going to perform in the same way, even though it was optimized over this particular data set that we gave it. This is essentially modeling methodology. It's how we define the problem. There's a lot of steps here that are outside of what we'll really focus on and talk about today. Before you even get started with your machine learning problem, you should understand the problem you're trying to solve. And if modeling that is the right way to solve it, and how you're modeling it, and make sure that you're modeling it in a way that is appropriate for the problem that you are actually trying to solve. After you've done all of that and you've identified your data set and you've prepared your data set, what we're going to talk about today is how to split our data set into training and evaluation sets and the proper methodology to that. I have a very opinionated perspective on this that is not always emphasized as heavily as I think it should be on the interwebs. And so we'll go through my very opinionated opinion on how to separate into training and evaluation sets. And then, of course, we've already talked about algorithms, so you know how to choose the correct type of algorithm, define your problem. Is it regression? Is it classification? Choose your algorithm. We may touch on, and then at the end, I think we're going to try to touch on pre-processing your data, which you could consider it prepare and clean the data set, or you could consider it perform machine learning optimization if we're talking about cross-validation. So those are the 2, 3, and 6 is where we're kind of focused today. So generalizability, just to hit on this one more time, you guys should really understand the concept of model generalizability behind the end of the course. I think I've said this in almost every class. Probably will be a test question. It's the model's ability to perform well on unseen data, on data that's not part of the training set, on data that exists in the real world. So how well does your model's performance broadcast to the real world? It's important because that's what we care about. I don't care how well your model does on your training set. if you put this in production and it doesn't do well in production, that's what I care about. Like, that's at the end of the day, your performance on your training set really doesn't matter at all. So it's how well is it going to do in implementation? And we have to be very careful here, because we can trick ourselves into thinking that it's doing better than it is. And that's what we're going to talk about today when we talk about train test split. This is a reminder to myself. So I'll give you an example of something that does not generalize. So when I was one of my companies I worked at, we did programs for the community, and these kids would come in and we had a career day, and they could learn about how to be a data scientist and what being a data scientist is about. And we thought, well, these are middle school kids. They're probably not super interested in most of this stuff at this point in their life. Let's try to create something engaging for them. And so what we did is we trained a model over a data set we had found online that was given some information about an individual. Can you predict their song preferences? And we trained a model, and it performed pretty well. And when these students came up, we asked them to volunteer and to go up to the front and type in their information and see what the model predicted for their song preferences. And it turned out, we did this intentionally, that the model was very, very poor. And they laughed and they thought it was funny. Like, every time the model would say something ridiculous about their song preferences. So we showed them the data set and we asked them to explore it and maybe come up with some suggestions why that model was so wrong. And then as they dug into it, they said, oh, lo and behold, this data set is only from people in Switzerland, and it is one very specific school in Switzerland. And, so this is a model that doesn't generalize. It does not, it's a data set that's not generalizable, really. But if I was to ask the model, from a student in Switzerland to put in their data from that very particular school, it would probably perform pretty well. So that's generalizability. Obviously, your data plays a very, very important part in that as well. So as you're defining your data set and defining your problem, you have to make sure that the data you're collecting is really applicable to what you're trying to predict. I'm trying to think if I should say one more thing on that. I will not. We will move on. So what you guys have been doing in some of your homework assignments for extra credit, because today's the first time that we've actually talked about it, is something called train test split. So this is our solution for assessing the performance of our model, because we know that we can't assess the performance over the training set. We know that's biased because the model has seen that before. That'd be like giving you a practice test, and then you come in for the test and I give you the exact same test and you say, well, I've seen all these answers before. So we want a different test that's not the practice test. And that is our test set. So when we create in machine learning, you'll often hear train test split. It is a very common way that people refer to it. And what it is we have this full data set here, all of our data, and here's all of our columns, all of our features, and you can think of this kind of like an Excel sheet here. So here are all of our features for each observation. Each observation is a row, is an individual, or is a house that we're trying to make a prediction on. Here's our target column. It's a one-dimensional vector. When you do train test split, you split into X train, Y train, and X test, Y test. So we have a smaller set of observations, of course, all the same features. And of course, we have the matching Y pairs for that. And you do the same thing in X train. And then this is used for model training. And then the the test set here is used for evaluation. The point of the test set is that is the data set that tells you how well it will perform in the real world. You do not use it to train your model weights. You use it to assess how well your model performed. Here is my very opinionated thing that I will give you. The test set should only be used once, exactly one time. And that is the second before you deploy to production is when you say, all right, I'm going to run and see what my performance is on my test set, and you've used it exactly once, and that's it. And so naturally you might say, well, that seems challenging because I know there are these things called hyperparameters, which we just started to talk about last time in Random Forest. We just at the very end of class started to talk about, not the one yesterday, but Monday we started to talk about, hey, we've got, number of estimators, we've got max depth, and we can define all these parameters, and we can train all these models, and we can get a performance metric for them. And in your head, you very naturally might be thinking, well, we can compare all those models to the test set, right? And that tells us the performance. No. You can, one time, when you select your final model, your final hyperparameters, this is the holy grail, then you compare to the test set and implement. So we need another data set, and that's a validation set. So I strongly recommend something called a train validation test split. Now, most people just say train test split because nobody wants to say train validation test split. It's just too many words. But know in your head when people say, hey, I ran train test split, it's very likely that they actually created a validation set. Maybe they created 2 validation sets. Maybe they have a lot of data. It just depends. It really depends on how much data you have to do this. There are times when you can't create a validation set because you don't have enough data. That's a sacrifice you have to make. And you just have to accept that either you're going to bias your predictions by using your test set more than once, which I would highly recommend against, or you're just going to use your test set once and you're just going to have to make the best decision you can with your training set using something called cross-validation, which we'll talk about in a bit. So train validation split, it's my highly recommended and preferred method where maybe 60 to 70% of your data is in your training set. You could get as low as 50%, but then you might not have a good representation. You could miss a substantial sample size. Validation set, maybe 10 to 20%, and your test set 10 to 20% if there's room. 20% is getting pretty high there. You can have a smaller test set than your validation set. So so in this picture here, this is a good representation. You train your model on your training set, and then you evaluate your model on your validation set, and then you tweak it, maybe according to some output. Maybe you change your parameters, try a different model. So you make some adjustments, and then you train it on your training set again, and you evaluate it on your validation set. And you continue to do that until you have your perfect model here, and you say, this is the one I'm going to put into production, and then you put it into production. Okay.
When you put into production, do you then use all the data or so to stay? Okay.
Yes, you hit a good point that I wasn't sure when to insert this information, and I was going to do it later, but now that you brought it up, I'll bring it up now. The answer is yes. So when you train your model, here's my very opinionated recommendation here. When you train your model of your training set, follow this loop here. Train, evaluate on validation, or really evaluate on cross-fold validation, which we will talk about here in a moment. And then when you're trying to decide, use cross-fold validation to evaluate hyperparameters. When you're trying to decide between models, like I have a random forest and a logistic regression and a neural network, you're trying to decide between models, then use your validation set. So you've got your final model here for your validation set. Train that, combine your validation set and your training set, and don't change the model parameters, retrain it, and or give it all that data. Then predict how that will perform with your test set. Your performance metrics will go down. That's okay. We want a realistic number, not the best number. Predict with the test set, Then take the test set and the validation set and the training set, give your model all of that information, then deploy to production. Okay. I should put that in words. I will do that. That was a lot. I was going to say that later, to be fair. So why do we split into 3 data sets, at least 3 data sets? This is going to prevent from us creating a model that's really overfit to our training set that really follows like every niche data point, because we're taking we're comparing the model to data it's never seen before. So we're making a model whose weights and biases will broadcast to that unseen data. And the reason we need a test set, that lock and key, only use one set, is because it allows us to get a sense of how well this model will perform on completely unseen data, new production data. Without that, we have no idea. And if you use your test set more than once, the reason I'm telling you not to do that, because you won't mean to, but you will accidentally be selecting parameters that make your model tuned to that test set. So you're not helping yourself with the overfitting. You will get overfit. And then what happens when you implement it in production is your performance will be much lower than what you evaluated it to. So I recommend you only use it once, because that's going to give you the highest performance metric closest to what you will actually see in production. So it's a more realistic number. You're not going to have an oops moment where stakeholders say, you told me it was going to perform at this amount, and now you're 10 points below that. That's a big difference. So that's why I recommend that. Hyperparameter tuning is important. That's why we split into 3 data sets, so that you can have something. That's why we have that validation set, which you can use multiple times to have something to compare hyperparameters or different model approaches or entirely different methodology approaches to each other. Okay, that's for you guys, summary slide.
When you're doing it, do you have a built-in method for it, or do you have to run the train test split one that's already built in like twice to make the 3 data sets?
Oh, that's a good question.
Create it?
I can give you some code for that.
Okay.
sklearn, I bet you a fair amount of money that within a year, sklearn will have updated their train test split method to make 3 data sets. But they're a little behind at the moment. So when they did release that, it does only split into 2 data sets. So it is a little funky. You have to do it in 2 lines. You have to say, hey, train test split, give me one data set that's my training and validation set, and one that's my test set. And then you have to train test split your training and validation set into 2 data sets. I will share that code with you guys. Of course, when you're working with the sklearn data sets, there are probably only like 100 records in there. You really probably can't train test validation split those, but.
In the real world, let's say you get to the test set and it's abysmal, it's awful. Or you're done, or do you just go back and do you resplit with a random new split and retrain?
That's a really tough spot to be in, and it sucks. And what that means, if you get to the test set and the evaluation metric you get from that was very different than what you got from your validation set, there was something wrong when you split the data, or you overused your validation set too many. Like, there is a limit to how much. You shouldn't be choosy. Try not to use your validation set too much. I actually don't recommend using it for hyperparameters. We'll talk about cross-validation, which I would recommend for hyperparameters. I only recommend it for different approaches, those higher level things. But if you get to that point, I would say you should have known before that you were going to get a bad metric. And if you were really, and if you knew before you were going to get a bad metric and then you still got a bad metric, that's your test set performance will always be less than your validation set. So if your validation set's giving you 0.6, your test set's going to give you, 0.55. But if you had great performance, if you had a 0.9 performance on your validation set and you got to your test set and it performed at like 0.7, you split your data wrong. There's bias in your data. Those are not equally represented data sets. And there could be a very real thing that happened in that. And it's probably, if I had to guess, the first question I would ask you is, what's your class imbalance? What is the, which we will talk about, okay? So we will talk about class imbalance today. What could be happening is you have a very low signal. Let's imagine our fraud use case. Only 1% of people are fraud. 99% of people are not fraud. When you do your sampling, because it's just random sampling, I'm just choosing random sampling, it could be that when you create your test set, only 0.2% of people are fraud. And it could just happen that you put 80% of your fraud people in your test set on accident, just by random sampling because of the low signal. And that's a heavily imbalanced data set. And your population that is in your training set and your validation set is not the same as the population that is in your test set. Okay, that was a long answer to a very short question. I apologize. Time-dependent consideration. So I will caveat here that another thing to be mindful of, in addition to the representation of your data, is if you're working with temporal data sets. If you are working with a temporal data set, meaning you are trying to predict something that happens the next day and the day after that, if your data set that you contain, that you give to your model, has multiple days in it, think the stock market, okay? We're trying to predict the stock market. There are a lot of people who might claim, I can train a really good model to predict the stock market. I've predicted the stock market. Look at my test set performance metric. But sometimes if you dig into that, what you might actually see is they didn't consider the temporal nature of their data set. And so what they essentially did is they cheated. Their model can say, hey, I see what happened to all these other stocks on this day. And so I can imagine that this stock that you're also giving me is probably also going to go down. So you cannot give your model future information. It will just use the patterns in that information to cheat and give you a good answer. And then you try to implement this in the real world. And of course, it doesn't have all the information. It doesn't know how all the other stocks are going to perform tomorrow. Nobody knows that. And so your model will perform poorly in the real world. So do not cheat and give your model, just really think about how you're splitting your data with temporal things. You have to put a lot of thought into it. And there's a lot of great resources and papers, and I'd recommend you guys dig into that. There's a ton of different approaches, but here's one in a picture on the left here where we have days, and you can see that in this cross-validation technique, they're combining days previously but never after. So that's what they're not looking into the future. They're only giving the past, and then they're saying for your test set, tell me your prediction for the next day. And then notice they're dropping these out. These two folds here are not considered at all. And then they're sliding that window over through training and validation and a test set. So just a chronological split may be important if you're trying to predict. I'll give you guys a real world example of something that I built. We were trying to predict, will somebody's policy, lapse in the next 90 days? So our target variable was into the future. So when you, in addition to when you creating your train test split and being careful with that as well, you also have to make sure when you're creating your training data that we are backdating our people. So we're looking at what did these individuals look like 90 days before they actually lapsed. Before they canceled their policy. So otherwise you are sort of artificially training on what they look like now, not what they look like at the time that you're trying to make the prediction. So all those things, very important. These are all the gotchas. Some common, again, gotchas, data leakage, we talked about that. It's that's where you're cheating because you accidentally gave it more information than it should have, and class imbalance. We'll talk about that one a little more. So, okay, so what does this have to do with generalizability? You started with generalizability and jumped to train test split right after that. Well, train test split enables us to create models that generalize. I hope that's clear to you guys now, that that's the point of this. If we set aside a test set, it can kind of simulate. It's sort of a simulation. We're creating a simulation, and we make our test set represent what we think it will be when we implement this in the real world. And so we can say with confidence how it's going to perform in production when we actually release this. So it makes it, it enables us, it doesn't make it generalizable, but it enables us to assess the generalizability, and to put a hard and reliable metric onto it. Okay, and I said, hey, I would actually recommend using cross-validation. This is cross-validation. We're gonna spend a minute really getting to know cross-validation. It is very, very important, and really, really common technique, and it's gonna serve you very well. So it's a statistical technique used to take a data set, your training set specifically. In this case, imagine we've already done train, validation, test split. Validation and test data sets are sitting somewhere else on our computer. When you see data set over here on the left, this is just your training set, okay? And if you see the word test in here, we're not actually talking about the real test or validation set, so sorry for the terminology confusion. But when we're talking about cross-validation, we're only talking about your training set. Okay, so now that we're focused on this, I have a picture later that shows this all together. But now that we're focused on this, instead of just overusing our validation set that we've created, we're going to try our best to use our training set. And we can do that by creating mini train test splits, and then training multiple models, training the same model over these different splits, and then averaging the performance. So essentially what we do is we take this same data set and we copy it 3 times. We copy paste the data set 3 times. So these are 3 representations of the same data. So the same person is in fold 1, fold 2, and fold 3. I actually call these iterations, not folds, but the training data set, then when we train the model, let's say we have a random forest model and we want to test whether n estimators of 50 is better or n estimators of 100 is better. And so when we say n estimators equals 50, we give that model to this one, and to this one. We give all 3 of these, n estimators equals 50. But we only give it to this training portion. Give it to this training portion, and this training, we combine these 2 and give it to it. We give it to this training portion. And then this little test segment, we take that out and we evaluate. So we train on this, evaluate on this. And then we slide our test set to a different fold of the data. See here? We train on this and this together. We evaluate on this segment. We train on this segment and we evaluate on this segment. So then we'll get 3 different performance metrics because there are 3 different test sets and 3 different training sets, and we average those together. The average of those is the performance of our model on n estimators equals 50. We do the same thing for n estimators equals 100. We compare the 2, we see which one's higher. Okay. I think it's good for you to be aware that there are different types of cross-validation. We will only talk about one because the second one is just an extension on that one. And I don't really see any point in leave one out cross-validation. It's unnecessarily computationally expensive and less powerful. So, but it's good for you to know it exists. So we have k-fold cross-validation, which splits into k-folds. That's what we just talked about. These are 3 folds of data that it's being split into. And the most, I'm trying to decide if this is the right time to talk about this. Sure. The most commonly used values for k, by the way, are typically odd sets of odd numbers. So 3, you would not do k equals 2. I have never seen somebody split into just 2 data sets, but k equals 3 if you have a very small data set. If you have enough data, k equals 5 is probably the most commonly used value. 7 is another very reasonable one if you have a lot of data. I personally have not really used 10 because you got to be working for a really big company or working on a really large data set to split into 10 and still get a good performance metric out of that. But 3, 5, 7, 10. And then leave one out cross-validation is very similar to the approach that we just mentioned here. But instead of splitting into like equal proportions, 30% of the data set, 30%, 33%, 33, 33, what you would do is you would literally take one record out, train over the entire data set, evaluate on that one record, and then you do that for all the records in your data set. So we'll not be talking any more about that one. Stratified k-fold validation. Remember I said, hey, you said, hey, I built this and I evaluated on the test data set, and the test data set metric was very, very different from our training and validation metric. We didn't expect that to happen, and we dug into the data, and it turned out it was a fraud problem, and the amount of values, the representation of the data was different in the training and the test data set. Stratified k-fold validation, stratifying your data, is how you solve that problem. So if you have anything greater than like a 60-40 split, like if you are working with data that's like 70-30, 80-20, and when I say split, I'm talking about a binary classification variable here. So I'm saying responded, didn't respond. You could, of course, broadcast this to multi-class or anything that you're trying to predict. But for classification tasks, but if you have class imbalance, which I know I have slides on a little later, so I'm ahead of myself a bit here. Stratified k-fold validation, there's an sklearn package for this, is how you solve this. And what it does is you tell it what your target variable is. It looks at the representation, say it's an 80-20 split, and it makes sure that that target variable is an 80-20 split in your training set, in your test set, and in your validation set. So the proportion that you see in the train test split is the same. It's stratified, essentially. It stratifies on that. It splits on specifically that metric. Okay, metric, that column. All right, let's talk about k-fold validation, how k-fold cross-validation works. In this picture here, we have different iterations of model training, and we have split the data into a series of folds here. We have split the data into 5 folds. So the first thing you're going to do is you're going to divide your data set into k equals folds. Notice, you'll notice a pattern with the use of k in machine learning that represents typically n, like the number that you put into your model. So k is equal to 5 here. And so this is one fold. It just means it's, the first fifth of the data set. And this is the same people as this one, as this one, as this one, as this one. So these are exact copies of the data set in this picture. In reality, you don't necessarily exactly copy the data unless you're doing parallel compute, but you could if you were going to do parallel compute. So we have 5 copies of the data set here, and we have 5 different partitions of the data set. In the first iteration, so we do iterative training of the model. So we're trained over K-1 folds, and we validate on some holdout fold. We choose one of the folds, and we set that aside, and then we use that as our test set, our validation set, evaluation set, maybe I should say. We use that as our evaluation set. You can see that this test set slides folds each time. So it's a different fold that we use in each iteration. So we have a different fold used for evaluation. So we complete this K times. So if I tell you, hey, this is in your K-fold validation, you're using K-fold validation where K is equal to 5. What is the, how many errors are output before you average those errors? It would be 5. You would have 5 different model errors so you get the error of this model, the performance of this model, your accuracy or whatever your metric is, whatever metric you've defined, you get that metric here, 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 and here. So you get it for each run, each iteration of training and test sets. And then you divide that by 5, divide that by the number of K. So you get your average error across all of these folds. Let me pause there for a second. Any questions on K-fold validation?
Are we copying the data set or are we defining the data set to the K?
Let me see, both. I think I'm gonna whiteboard this. So let's talk about, I found last time it was very helpful if I put actual data on here and then you guys could see it. So here's our data. I'm gonna put an ID column on here so we can have an ID. And 1, 2, let's see, I know we're going up to 5, so we're gonna go to 10, just so make a point. And let's do x sub 1, x sub 2, and y. Okay. A, B, C, A, B, C, A, B, C, A. Oh, there's something along there. Okay, so let's talk about threefold. Threefold validation. So in threefold validation, flip back to my. You know what? I'm gonna stop sharing because it's probably hard for the. There you go. I think I can change this view here. There we are. Okay, so in threefold validation, what we are going to do is we're going to take this data and split it into thirds, and maybe I should have done 11, but this will be fine. Let me take a different color. Okay, so we have this third, we have this third-ish, we have this third-ish. So when we go to do if I was to draw it and make the picture similar to that photo, we would have 3 sections, 3 iterations of the model that we're going to train. And we would have 3 folds. If this was fold 1, fold 2, fold 3, fold 1, fold 2, fold 3, sorry, fold 1, fold 2, fold 3, and fold 1 would contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so this is iteration 1. And iteration 1, we tell it, hey, you can use the 1, 2, 3, and 4, 5, 6 for training. And this you have to use for test. You can evaluate how well you did on record 7, 8, 9. And then we get a performance metric in, let's say it's 0.7. And then we're going to say, hey, for training, you can use 1, 2, 3, and 7, 8, 9. But for test, I want you to evaluate how well you did on 4, 5, 6. And let's say for some reason it just bombed it. Like we got a 0.4. And then for this one, you can use this for training. And we told it, hey, you have to use 1, 2, 3 for test. And again, it got a 0.7. And then you would add these 3 together and average them. So you would do 0.7 plus 0.4 plus 0.7 divided by 3. Does anybody have that?
One point eight divided by 3, so was 0.6.
6?
That sounds right.
Something to that effect? Okay, so it's both, if that makes sense. So this was iteration 1, so essentially this is model 1. Iteration 2, model 2. I don't want to call it model 2 because they're the same parameters. Iteration 1, iteration 2, iteration 3. And when I say they're the same parameters, what I mean is this is the same model. So if your model parameter is like n estimators equals 50, they're all getting the same model parameters. So n estimators equals 50 here, 50 here, and 50 here. So it's the same parameter, and then this is your final output. You would run this entire same process for n estimators equals 100, and then you would compare this to what it was when n estimators was 100 across all these different iterations. So you're kind of getting an average. It's another play on that like wisdom of the crowd type of thing. You're shuffling the data, holding certain pieces out, and seeing if how stable that prediction is. Okay, so if we had 5, I'll do this one really fast. Idea there. So if we had 5, this will go that's 1, 2, 3, 4, 5. We have 5 iterations. So we say n estimators equals 50, and we pass it. We train a model on that 5 different times. And 1, 2, 3, 4, 5. And in this case, this is why I said if you don't have very much data, do smaller splits, because now this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. I won't write that each time. You get the idea. Dot, 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 right across all of these. So now we only have 2 people in each data set. So you're slicing it up really small. And then you have a number here for each one, a performance metric. And we would average the sum of the numbers divided by 5. All right. So let me share my screen again. Excellent. We are, let's see, 59. When might be a good time? I'm going to do 2 more slides and then we're going to take a break, okay? So I promised you I had a picture representing all of this kind of together with the training set. I wish there was a validation set in here as well. I should create a new one that has kind of everything that we've talked about. But this is a good representation. Just know that you'll have to put another little validation set in here. But so we have our original data set, and we split this into training and testing. Actually, we split it into training, validation, testing. Remember, I said I have an opinionated perspective, so the internet visuals don't always match up to how I think it should be done. So training, validation, testing, and you set both of those aside. Testing set is only used once. Final model evaluation. Evaluation set can be used multiple times, but I would recommend it only for choosing between different methods, choosing between different models, choosing between different approaches. Training set is then split into n folds, in this case 5 folds, and you perform cross-validation on your training and what I might reterm as your evaluation set. Train, evaluate. Not to be confused with your validation set. And what I would use this to do is to tune your parameters or tune your hyperparameters of your model. So when we talk about n estimator, should I use 50 or 100? When we talk about max depth of a tree, should it be 15 or 32? Those are the parameters that I would use to select in cross-validation. And then when you're comparing, well, I have a random forest and I have a logistic regression, which one's better? Then you use your validation set. Opinionated approach. All right. Last slide, and then we'll take a break. So I think you guys understand this based on the visual before, but this is just to reiterate. Sometimes people get confused. Well, what's the difference between cross-validation and train test split? Why are they there, and what's the difference? You guys understand that cross-validation is a subset of your training set after train test split. So train test split divides into a training set to assess model performance and training and evaluation on unseen data. Cross-validation is part of the model training process, but it's a way we split our data so that we can select our hyperparameters. Okay. Let's take a 10-minute break, come back at 7:12, and at 7:12, we will talk about the promised class imbalance. Okay. Apologize for the delay in getting started here. We were discussing a really interesting problem about comparing similar comments to each other. So an individual makes a comment on a page, and there's lots and lots of comments on this page, and maybe their comment is similar to somebody else's comment, and we want to direct them towards that comment that it's very similar to. How do we assess sentence-to-sentence similarity? We're going to talk about at the end of class, if you guys are bored, we're going to talk very briefly, unplanned, we'll stop the recording, about cosine similarity, glue score, and RAG architectures for large language models for document referencing, if you guys are interested. Okay. But for now, we're going to bring it back to the basics of model building and start with that, which class imbalance is a very, very important concept and oftentimes overlooked and causes catastrophic problems with your training your model and with implementation and production. So I've already said this a couple times. You guys probably already know what it is, but just to be 100% clear, and I just wanted to make sure, okay, you guys are all good and can see everything. Sorry, wanted to make sure I unmuted. Class imbalance is when one of your samples in the data set, typically your target variable that you're trying to predict, is extremely underrepresented. It makes up a very, very small proportion, anything under 40% really, makes up 40% or less of your data set compared to the other variables or other options. Of course, in the picture in the right, this is a binary classification problem where the majority is represented here in blue and the minority is represented here in orange. But that is, you can assume, you can expand this to a multi-class classification problem where you have multiple categories and your category you're trying to predict still represents a relatively small, relative to the proportion of categories you're trying to predict, a small portion of the data set. So that is what class imbalance means. One of the points of this class is to really just give you guys the terminology to search the internet. And when you go and look and read about things and people are recommending approaches, they say, ask, do you have a class imbalance data set? Now you guys can answer that and you can say yes or you could say no. Does anybody have any examples of class imbalance that you could imagine? Some imagined examples.
I remember back when like AI was starting to get big and they would create the images and then the differences between the white where they saw more often compared to people of other races where they didn't have enough data to give an accurate representation. And that was a thing for a while.
That is an exact example of class imbalance. So that's an underrepresentation of some type of class that you're trying to make a prediction on. And so, trying to make a model that detects whether people are smiling or not, and having only primarily pictures of white people smiling may make your machine perform very poorly on people that don't match what it was trained on. And that is a real risk that people need to be aware of as we train these models, as we use large language models, as we use AI and ChatGPT, because that same bias of only models make decisions based on data, based on history of data. So this is similar to class imbalance. So sorry if I go on a tangent here about model bias, but I'm going to go on one short tangent here. There was a famous study that was done on resumes, and this is a bit old now. This is some time back, but still very relevant. And they had two resumes, and they looked exactly the same, word for word. Exactly the same. The only thing they changed was a male name and a female name, and the model recommended the male named resume over the female named resume. And that's because not intentional. It's just when you look at history and the hiring practices, there were more males that were hired into that role than females historically back in time. And so what we have to realize is that our historical representation of data may not always represent the way we want to make decisions in the future. And so we may have to manipulate the data as we train our models, do things like oversampling or undersampling to try to make the model make decisions in the ways that are maybe more appropriate that we would see. And also putting up gates for governance, for bias check. This is such a deep rabbit hole, I apologize, but there are policies and regulations now that exist at a state level and at a national level for how you have to adhere to model development standards when you put things and make decisions on things like a claim decision, or there are regulations out there. It varies across industry and it varies across state. So it might be worth looking into if you are, especially if you're implementing a model in a way that you might have questions about. If somebody from a regulatory standpoint might ask questions about how that's being implemented. So, all right, that was a tangent from class imbalance. Great tangent. There are some challenges that class imbalance presents. So if you don't address it, one is that you can of course make biased predictions because most of your model wants to be right most of the time. If you give your model a data set and you give it an objective function and you say be right most of the time, and you have a data set that is heavily imbalanced, it's going to say, well, how do I game this system? That's all computer machines do, is they try to game the system, and it will game the system by being correct most of the time. So being correct on the majority data set, and that can lead to inappropriate weights being trained for your minority data set, and it just may not be able to perform well on that. Or when it does perform, it could have a lot of bias. Your evaluation metrics can be very, very misleading. So we'll talk about this a lot more in the metrics class, but if you are working with the fraud problem, for example, and you're using accuracy, and you train a model and it's 95% not fraud, 5% fraud, and you train the model to predict fraud and you use accuracy, you can actually achieve a 95% accuracy without detecting any fraud at all. You just predict 0 for everything. You just say there's never any fraud, and technically speaking, from a metric perspective, your accuracy is 95%. And this is why you guys need to have a lot of I don't want to say suspicion, but you should have sort of a gut reaction when you see a really high performance metric on your model and question how it was able to achieve that, and really explore that, because all models are wrong, some are useful, but really high performance metrics don't necessarily come easily. So if that happens easily, question that, and it could be something like this. You have class imbalance, and your machine's found a way to game your system, game the game that you presented to it in a way that you didn't really intend. So they do exactly their objective function and nothing outside of that. Poor minority class performance, we talked about that, okay. Great, so what do? You can't just, I won't give you a problem without a solution. So the problem is there's class imbalance, and here is the solution, or a suggested approach. This is Introduction to Machine Learning. So there are many, many more approaches. I could say much more on this, but I'll just name these 2, and I'll actually add a third one, which we talked about earlier. I should have put it on this slide. I apologize. Oversampling, undersampling, and stratified cross-validation and stratified train test split. So stratifying your data set when you split it, whether that's train test split or cross-validation or both, and then applying either oversampling, undersampling, or both. Okay, so oversampling. Oversampling is here on the right. And let's imagine we have this original data set where blue is everything not fraud, orange is fraud, it's a smaller representation. What we can do is we can just duplicate this. Let's just boop, 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 let's make a bunch of copies until the representation is the same as our other data set. Of course, you're going to violate some assumptions of those traditional machine learning models where we talked about, hey, we're assuming the same person doesn't occur in there more than once, but this is one approach, and you don't necessarily even have to go up to 50-50. You could go up to something more reasonable. You could do like up to 40-60 or something, where it wasn't at least 10-90. So that's oversampling. The other side of that coin is you could do undersampling. And sometimes this might make more sense, where you say, hey, I've got just a ton of people that I don't need all of those people in my data set. A lot of them look the same. That's a situation you might want to undersample. Have a lot of people, a lot of them really look the same. They behave the same. They're not really that different. Can I undersample so that these two classes have the same proportion or at least a more reasonable representation? You don't have to get to 50-50. Again, at least maybe get to like 60-40 in a set. You can, of course, also do both. There are techniques that combine oversampling and undersampling. You don't have to choose one, but now as you guys go to implement that, you at least have context and understand what this is. When you're doing this undersampling, on the break, we were talking about clustering, we were talking about unsupervised learning, and I chatted about a approach that I had used that was actually useful in sampling, where we had a lot of documents and we had a task for individuals to manually label those documents, and we had thousands and thousands of them and not a lot of time. And so what we did is we did clustering, and we grouped documents together, documents that were similar to each other. And then we did subset sampling from the clusters. So say we had 10 clusters, we took 10% sampling from each cluster, so that when people were labeling these data sets, they were actually labeling like a diverse set of data, instead of if we just did random sampling, they would have labeled just all of the majority class of our data. And we wanted a really diverse set for our model. It was a very useful application of clustering. And you can do the same thing here with undersampling. So you can use clustering to group these individuals together. You could use unsupervised clustering, group people together, and then do your undersampling by only pulling from people of these clusters. So pulling 10% from cluster 1, 10% from cluster 2, 10%. That way you still have good representation within your class here, your majority class, but you're kind of dropping off all of the people that are sort of the same. So you're getting diversity. That's what you want in your model. You want it to have a diverse enough data set that it has seen, and it's like growing up, it's seen some things, it's experienced some things, it knows how people behave in certain situations. So, okay, any questions on class imbalance? Perfect. All right, baseline models. Again, this is sort of a modge-podge of concepts for you guys to be familiar with. So it's not quite as smooth as just talking about all the steps in a random forest. But baseline models, what's important here is in programming, there's this concept called KISS. You keep it simple, stupid. So it extends to many other things, and machine learning is no exception. And when you build your model, do not try to implement a random or a neural network first. Don't have that be your first model that you build. If you can solve it with a simpler, a less complex model, you will be better off. So try a simple model first. Try a linear regression. Try a logistic regression, and just train it. Get your data out there. That's your baseline. So, that's an initial model for you to just start from. And then once you have that initial performance metric, you can easily say, well, now my next model had this much lift. I got, 10% lift by implementing a neural network. Without training a simple model first, you really don't have a point of reference for how good your model is. It could be performing worse than that, is what I'm saying. So starting with a simple model, simple is always better. It's going to be more cost effective. It's going to be faster to train. You have a greater amount of transparency in how those models make decisions. They're more interpretable or more explainable to your stakeholders. So you really only want to give up those trade-offs if you're getting higher performance. So higher performance or those neural networks and those more complex models are really not better if you're getting the same level of performance. Just go with a simpler model. You get more benefits from it. There's one more thing to say about baseline model, which is even before that step. So I would really call that like your version, your beta model. Maybe I would even call that your beta model. Before you even get to a beta model, you should have some conceptually understanding of what random means in your problem. So for example, we have two classes, a binary classification problem. We have, let's do fraud. Fraud, for example, if our model only predicts, fraud's a bad one because it's class imbalance. What if we're trying to predict whether a coin is going to land on heads or tails? Okay, this is relates naturally to our understanding of probability. And I give you all this information about a coin. I give you the airspeed in the room. I give you the gravity that we're at. I give you the barometric pressure. I give you like the weather prediction for the day and what time it is. And I tell you that I can predict whether a coin is going to land heads or tails with 50% accuracy. And naturally you're like, well, I mean, it is 50-50. You're really not doing pretty well. If you told me you could predict it with 90% accuracy, I'd be pretty impressed. So understand what random means in your problem. It's not the same. Sometimes it means 0.5, sometimes it doesn't. And so if you have a model that is performing close to random, then that's not a very good model. And you should realize that it may not be worth going through all the work to implement, or you should invest more time in making it better. And maybe that means getting more data. And maybe that means, it's not always just a selection of the right model and the parameter. Maybe your data is not informative. So understand what average prediction. So for a house, for example, for regression, maybe you might just use the mean or the median for houses. Median makes more sense because mean is going to be heavily skewed because a lot of houses there's going to be some houses that are like absurdly expensive, like $12 million. So it's going to push that mean higher. So median, you can use that as like a performance. So what if every single house you gave me, regardless of what the house was, I just predicted the median house price? What would my sum of squared errors be? The house value minus the median for every single house. So then you have a baseline metric. So when you implement you train a linear regression model, it should be better than that mean prediction. So you guys for assignment 1, I believe you built a model to predict the price of the house. And one question you might have is, how do I know how well my model is doing? I heard you guys say, hey, this is a squared metric, but I'm getting billions for my squared error. And the goal of that assignment was not to train a good model, to be clear. We're just understanding the points of programming a model at this point. But if you wanted to answer that question, you could create a function that just always predicted the median house price, and then compare that to your model, see how much better it is. And that'll tell you if your model is informative over what I would call a baseline. So establishing a random baseline is really important for real world implementations. Okay, now you guys, I think, are probably starting to take these steps and put them into a process. You're probably, we've got a lot of pieces here. We've got trait test split and cross-validation and baseline models, and then you have to retrain it and evaluate again. And now we're starting to understand that machine learning is really a life cycle. It's a circular process where we start getting some data and we start acquiring a data set to put into our model. We do some validation and some curation of that data. We do some pre-processing, which we'll touch on in the third hour today. And then we train and tune a model. So this is really cross-validation, validation set. We're training and we're tuning and we're training and we're tuning and we're trying to find the best model. And then we get a model. And now we're going to analyze that model. We're going to understand what the feature importance is, how it's making those decisions, why it's making those probability predictions. We're going to get all the performance metrics for that model. And then we're going to validate it. We're going to run those performance metrics once on our test set. And then we're going to deploy that model. And we're going to put that into production. We're going to see how well it does. It's going to run for a while. We're going to collect feedback. That means that if you are trying to predict whether a policy is going to lapse or be canceled, somebody's going to cancel their policy in 90 days, you have to wait at least 90 days after your model implementation before you get your first piece of feedback. So just realize there's a delay based on, it's all dependent on how you set up your problem, how you set up your approach. Whether you're going to get immediate feedback, there could be a delay in feedback. Then you start, once you hit that mark, you start collecting feedback. And then you start assessing how well your model's doing in the real world. Over time, models do something called degrade. It's sometimes called model drift. And what that just means is that the world changes. Think of the world 100 years ago. It's very different today than it was 100 years ago. And that happens at a micro level with our data as well. So if you look at a model over time, your performance will actually go down naturally because people are changing, their behaviors are changing. The data that you use to train your model is different. And we are working with something called an offline model, which means we train this model sort of on a static data set, and then we put it into production, and it's not learning over time. It's not updating its weights each time. It's offline. So it's just a static object that has some predefined weights that we define within a training process. Everything in this class will be offline. Maybe in a more in-depth class, we can talk about online learning and reinforcement learning. So after a while, after you've collected some model feedback, you start to see your performance go down. It's time to retrain your model. It's time to go back through your process. Maybe you even add more data, and then you do data validation and pre-processing, and you retrain your model on that new set of data. So every at least 3 months, 3 to 6 months, 6 months is a long time, need to retrain your model to update it. Kind of depends on how you're implementing it.
How can you tell when a model is past the point where it needs to be?
Yeah.
Maybe it's sooner than, do you keep your baseline score there and be well, if it gets to the baseline, then we need
That's a good question.
Or do we get 10%?
There should be a threshold that you should define with your stakeholders and with your technical professionals when you implement into production. I'm not comfortable with my model dropping below 70% accuracy. You should have a alert, and you should determine how you're quantifying that. Is it 2 records? Is how are you defining accuracy? So you want a fair sample size. There naturally are dips and things over time, and things go up and down. So a reasonable way would be some type of moving average over a rolling average over 2 or 3 months. And that way you can do away with things like holidays or call volume having unusual impacts on your model performance. So a rolling average over a a couple of months, a window of months. And if you start to see your metric go down from, and when I say your metric, it's based on that model feedback. So you have a model prediction when you're in deployment, and it says, I think this person's going to cancel their policy. Did that person cancel their policy or not? So when that model feedback is, oh, it's been 3 months, they didn't cancel their policy, you were wrong. So that's what that model feedback is, a rolling average over a series of months. Of course, depends on your implementation. If you're working at a huge corporation, there are reasons why a rolling average over a couple of hours could be reasonable. So it just depends on the amount of data you're working with and your application. But I speak generally to where I think most of us are. Okay, so this process, this is just kind of like a conceptual process. When you actually go to implement this, and I imagine you guys will talk about this more in the API class, I just want you guys to be aware that there's quite a bit of technical infrastructure that goes around this. This is Google's proposal for MLOps, how to serve a model in an operational process, how to do CI/CD for model deployments. So you'll probably have feature store, data analysis still, you're doing some model analysis and experimentation, and then you're deploying your model as code to a repository that then builds and tests packages and deployments, and you have your CI/CD pipeline this is actually the process that builds your model, where you go through data extraction, validation, data preparation, training, evaluation, model validation. And then when you have your final model, it probably gets registered somewhere that says this is the hash code of this model. This is how you identify this model. This is where it's at and what it's being used for. And then you probably serve this through some API layer, some prediction API layer. So your actual development and implementation of this can grow in sophistication, usually not with one individual, but with a team of engineers and developers, hopefully. Did you have a question? No, okay. Okay, underfitting and overfitting. Here's just another concept in the bag of machine learning methodology that you guys should know. When we underfit the model, we've trained a model that is too simplistic. So I told you guys, hey, try the simple model first. And you did that and you found that it was terrible. That's probably because it's making some really large generalizations about things that just don't represent reality. And this is an example of underfitting, where it's saying, hey, everybody on the right side of this line is a circle and everybody on the left side is not. And that is clearly not the right way to model, to create a decision boundary for this problem. It does very bad. You can see how many times it misclassifies. It misclassifies these two circles as X's. It misclassifies these X's here as circles. On the other hand, when you train more complex models like neural networks and other such implementations, they can get really good about making these complicated lines, complicated decision boundaries. They can say, well, in this one niche situation, I actually think it's a green X. And that can be bad. That's typically overfitting. And what you see with overfitting is when you train on your training set and you evaluate on your test set, it doesn't do very well on your test set because it mapped these very, very particular boundaries that really was just like an oddity in your training set and not generalizable. This is not a generalizable model when we talk about generalizability. And so what the maybe appropriate decision boundary, an argument could be made that this is an appropriate decision boundary, and that these x's being over here were sort of an exception to the rule, but in large quantities. They don't occur super often. All models are wrong, some are useful. It's not our goal to have the highest model performance on the training set. I want you guys to know that. The highest model performance on the training set is not the goal. The goal is to create a model off of the training set which performs really well on a test set that it's never seen before. So generalizability is our ultimate goal. And so this is an underfit model, an overfit one, and that is one that's maybe more appropriate. Expanding more on that idea of underfit, becoming overfit, there is a very popular, commonly discussed concept in machine learning and data science called the bias variance trade-off. And the bias variance trade-off really describes this problem where you can have high bias and low variance, and that's a bad situation to be in. But you can also have low bias and high variance, and that's a bad situation to be in. So as variance goes up, bias goes down. But as bias goes up, variance goes down. So what you really want to do is find the sweet spot here in the middle. And that's why they call it the trade-off, because it's usually this kind of like push and pull tug between the two. So what is bias? Bias is the average model prediction from the ground truth. So bias is your y hat minus your y. So how close were you to the ground truth? So low bias here is here on this target. If we look at this target, you can see that there's low bias. Look, we're really close to the center of that target. This is also low bias. We were really close to the center of that target. So we were close to the prediction of a house. Like our values, what we predicted for the house value of a house was close to the real world value of a house. That's low bias. Variance is when we look at all of our predictions, how close are they to each other? So this is very, very high, very, very low variance because the predictions are all very close to each other. This is high variance because there's some spread between these predictions. So they're, the distribution, there's maybe more standard deviation. So there's a greater spread in what we're predicting for those values. If you look at the minimum and your maximum value of house prices, if they're far apart from each other, you probably have high variance. If they're close to each other, you have low variance. So you can have all of these scenarios. You can have low variance and low bias. Obviously, we all want that. Certainly, that's the best outcome. But in reality, there's a trade-off between the two, if we're thinking realists here. If you have this one, high variance and high bias, something is wrong in your methodology. But typically, we have this trade-off between these two, where we have a low variance but a high bias, or we have high variance but a low bias. And that's what's represented in this picture here. I just think the target is sometimes a good picture. And right under here, you can even map the underfitting and the overfitting to these same concepts, these bias variance concepts. So this underfitting is on the left side of the chart here, where we have a very simple model, but it's not a very complex model. So all of our predictions are probably very, very consistent, but they're not correct. So there's a lot of bias here. There's a lot of bias in underfitting, even though our variance is maybe not very high. This one, on the other hand, there is not a lot of bias. We are exactly correct with our predictions. So we have an extremely low bias, but there's really high variance here in what we're predicting. And this one, of course, is maybe the appropriate solution that we're looking for. Any questions on the bias variance trade-off?
I assume there are things in like scikit-learn that will help
Hmm.
make these numbers, like do a calculation on this, or is it more?
That's a good question. Determining if your model is, you can make plots, will say, on your performance metric across your validation set or across your cross validation set, and how it performed on each, and you can compare those. And sometimes people can see when it starts to degrade, so you can make them with plots. I will say this is a little bit of the craft of data science, where you kind of have to inspect, yeah, and like play with it, your model a little bit, and try to really understand what the output is and what it's predicting. Visualizations, like that's why this is often visualized in a plot like this, because that's how people typically visualize it when they're training their models, is very helpful. What is the performance on the validations, on the cross validation set compared to the validation set, is typically what people are comparing when they compare the bias variance trade-off. And at some point, your cross-validation set starts to do really well. So it usually looks kind of like this. Your validation set and your cross-validation set are both doing poorly, and then maybe it gets a little better. And then at some point, your cross-validation set starts to do way better than your validation set, your holdout set. And that's where you're like, oh no, I've overfit my model. So it's sort of a visual thing. Though I bet if you search the depths of the internet, you would find somebody at Stanford who did a research project with some unmaintained code out on GitHub. All right, decision boundaries. I think you guys are familiar with this by now, but if not, I just wanted to throw this terminology at you so you're aware of it and can navigate it in the field and as you read through the internet. A decision boundary is how your model decides it's part of class 1 or class 2. And you can visualize these, which is really cool. And here's a data set, and there's several different models. There's a KNN, K-nearest neighbors. There's a logistic regression. There is a decision tree and a random forest. And sorry, sometimes I get very other things I want to tell you guys, but focus here. So there are, what I want to note here is that when we make this a decision boundary here, it doesn't just affect the points that are here. If we put a point way over here, it will be red. Or if we put even though we don't have any data to represent that. So the decision boundary, sometimes in other classes, I've showed these cute little pictures of circles. And then there's just nothing outside of that circle. I was trying to make a point with that, but now that we've moved a little further in this class, I want you guys to understand that decision boundaries cover all of the space. So there is never a prediction a model's going to get, or a feature observation a model is going to get that it won't know what to predict on, because the algorithm has told it. So these boundaries extend, essentially into infinity, or whatever the bounds of your problem are. So that's the part that I wanted to emphasize, is just when you train the model based on the algorithm, and whether it's linear regression, sklearn, logistic regression, it will have these boundaries that extend beyond what we see in the photo here. The part that I got distracted about when I paused is I think it's really neat that decision trees actually will always have this like step structure, because it's an if-else logic tree.
Right.
And so they're kind of binary, either go this way or this way. And what's interesting about random forests is while they are kind of that step structure as well, because it's a lot of trees making that decision, you'll get like weird little slices out of here. So you'll get slices like this out of there. But decision trees are always going to like cut your boundaries, decision boundaries, into squares. Okay. How do we feel about decision boundaries? Okay. This is perhaps an advanced concept, so I'm going to make you aware of it, but I won't ask you any questions in an exam or anything like that over probability calculation. I just want you guys to be aware. I think I wouldn't do you justice if I didn't make you aware of the distribution of probabilities that come out of your model. So sometimes when you train a model, let me take a step back. So imagine that you are training a model that predicts whether or not somebody is going to lapse. There we are. Going to that's a very common one. Whether or not somebody's going to cancel their policy with you or cancel their subscription with you. And I tell you that it's 0.4. So naturally in your head, you might say, well, that's a 40% probability, right? That means 40% of the time, people like them will cancel, and 60% of the time, people like them won't. So that means that if I look at my data set, that 0.4, and below, anybody below 0.4 represents 40% of our data set, right? But that is not necessarily the output from a machine learning model. So the reason I think this is important is because sometimes we might want to transform our probabilities to rescale them on a different scale. So when we hand them to stakeholders and people who are actually using those probabilities, it makes sense to them in their head. And when we hand them a 0.8, it means it will happen 80% of the time. When we hand them a 0.9, it means it happens 90% of the time. Sometimes our machine learning models don't put things on that scale. So if you look at like the probability predictions, it probably won't have very many above 0.9, and it probably won't have very many below 0.1, for example. And so a lot of these distributions can look like this, right? So in this case, we have this random forest where, look, there's a lot of probabilities over here near 0.1, a lot of probabilities near 0, not a lot in the middle. That is not an even distribution of 10% of the time it's 0.1, 20% of the time it's 0.2, 30. So to calibrate that, we would reorder these. It doesn't change their values. It just changes, you're not changing the order in which they occur. You're just shifting the values. It's like scaling them. You're like stretching them a little bit so that this is flat. So it's a uniform distribution. If that makes sense for your use case is what I'll say. Here's another one where, this is clearly making mostly binary predictions here. You might want to even that. This one's making a normal distribution here. And this is like a bimodal distribution here. So a calibrated one would be this dotted line here. Each of these colors corresponds to these distributions in this picture. A calibrated one would be this dotted line where 10% of the records represent 0.1, have a 0.1 probability, 20% of another 10% of the records have a 0.2 probability, another 10% of the records have a 0.3 probability. So that we're saying, hey, 10% does occur 10% of the time. 0.9 and below is 90% of the data set. When you have your model output, that is very likely not the case because that's not what it's optimized to do and what it's trained to do. You can scale your probabilities without changing the quality. It doesn't change the predictions or the quality of your model because you're not changing the order of any of those predictions. You're just shifting some of them over a little bit or a little bit this way. That's probability calibration. It's just important to be aware of because I found that as you hand people model probabilities, they just will automatically assume that 0.4 is 40%. So it can be useful to actually make it representative of that ahead of time. Okay. We're doing good. We're going to take another break. We are going to talk about pre-processing. I'm so excited. I was hoping we'd have time to get to this. Come back in 10 minutes at 8. 808. That'd be 808, yeah. I just saw your question, Jean. Does training with synthetic data points result in a more poorly trained model? And that's a really good question. Not necessarily. It depends on how you are. It depends on two things: how you are setting up and defining what performance means. So how are you assessing your model? I wouldn't recommend assessing your model on the synthetic data. So I wouldn't have your synthetic data be your validation set or be your test set, for example. So how you determine how well it's doing is really important. And then how you create your synthetic data in order to accomplish that objective, and what the objective is that you're giving your model to solve. So how is it determining success? How does it, what's your optimization function? How are you optimizing it? If you define those things correctly, and if you create your synthetic data in a very reasonable way, I think synthetic data can be a very powerful approach to augmenting your data with your model with more data in a situation where there wasn't enough data. So it doesn't necessarily train a poor model, but in the absence of good methodology, it could introduce some problems.
Okay, thank you.
Okay. Let's shut the banner off. Okay, pre-processing. I may whiteboard here and there or jump around in this one. I think there's quite a bit to say. What I want us to get to is being able to understand something like this and being able to implement this and at least understand the purpose for each of these steps. This is a very standard implementation of what it might look like to actually build a machine learning model from assuming you have data. So this doesn't include any of the creating of the data. This is a pipeline that creates your features and transforms them for input into your model, puts them into a grid search, does cross-validation, fits your model, gets the best parameters and gets the best estimator for you. So this is, you can use this template over and over and over again. I'll put this in the, I'll put all of these notebooks, by the way, in the class folder for this week. I haven't dropped those in. They're kind of some of these are a hodgepodge of things I've previously taught in the past. So this is what I want us to get to. And before we can do that, we should talk about pre-processing. So when we build a machine learning model, the data doesn't always come in a clean format. So very typically, if you just go get any data set from anywhere, it's not all zeros and ones for you. And some models can handle text input and can handle those types of things, dates, etc. Many models can't. So when we talk about linear regression, we did our y equals mx plus b. I'm going to do the beta sub naught plus beta sub 1, x sub 1 plus beta sub 2, x sub 2. We're multiplying things together. We're taking a number. We're taking 5 plus 10 times some number, whatever this number is from x sub 1, plus 11 times, I'll make these dots just so it doesn't get confused with the x's I have here, times some number, like number of bedrooms. Maybe that's 2. Square footage, 1,000. Okay, well, what if we have plus beta sub 3, x sub 3? What if we have color of the house? How do I represent color? I want to know, is it a white house? Is it a gray house? Is it a red house? Is it a pink house? Maybe pink houses don't sell as well as white houses. How do we represent something like color when it's looking for a numeric value to multiply by? Okay, so this is why we have to do pre-processing, because many of our models, like linear regression, because remember, logistic regression is just a linear transformation of this, so it's going to have the same issue. It doesn't magically get solved. Random forests also need this. They're numerical representations, even though sometimes online you'll see, you know, words. Is it a red dog or a green dog? It's what it's doing really. It's a 0-1 thing under the hood. So we need numbers. All right, everybody understand we need numbers. That's not to say some techniques can handle. You don't need to do this for all models that exist in machine learning, but generally speaking, this is the approach. Before we even get to that, before I jumped ahead of myself. Before we even get to that, of how do we take the color and make that a numerical value, maybe I should have swapped those around. Maybe that is the right spot to start. But instead, let's talk about imputation. So how to handle missing data. So let's imagine we do have something like number of bedrooms. So we have number of bedrooms, And we have, so we have bedrooms. And here's our ID. This is just like our people. And we have 2 bedrooms, 1 bedroom, and this one has nothing. And 6 bedrooms and 7. Well, how are we going to calculate our formula? How are our number of bedrooms, our value of 10, we're expecting to do 5 plus 10 times number of bedrooms plus 11 times, let's say this was 1,000 square foot house, let's say this QFT, say this had 1,000 here. We can't do our calculation. You might say, well, just put 0 there. Okay, well, if we put 0 there, then that's 10 times 0. And there's meaning in that, is what I'm saying. There are other houses in our data set that actually have 0 bedrooms and are, 300 square feet. It's a studio apartment here, not 3,000. It's a studio apartment. So 0 means something in our data set. Just putting 0 in there will probably make for a bad model, is what I'm saying. Your model's going to have trouble differentiating, deciding a decision boundary, because that's what it's doing. It's going to have trouble deciding a decision boundary to define the price difference between a house that has no bedrooms and 1,000 square feet and no bedrooms and 3,000 square feet. So we need to handle these, this is supposed to be a 0, sorry, not an empty 0. There we go. We need to handle these null values, these empty values. We need to do something with them that is reasonable. And this is, again, all of this methodology is where kind of the magic of data science comes, where your creative powers come in. So there are a couple different things that you could do. Of course, you could just use the most aggressive approach and just delete the data. So we could, and there are some reasons why maybe you want to do this. I'm not even going to X it out, but I'll do it on the side. We could just delete this row, and we could say, hey, don't train with any data that isn't missing. And you can do that. And if you're not finding an appropriate way to impute your data, you can do that approach. You guys know me now, and you know that I'm not going to recommend that because I think such things are going to occur in reality. And the problem is, if this is in your training set, it's going to be in your production set. And when that happens in your production, your model's going to throw an error, and it's literally going to say, I cannot handle this. And I think that's not a good way to build a model. So I don't recommend deleting them, deleting your data. You, of course, certainly can. What I instead recommend is something called imputation. So imputation is kind of a data science term. This would be one I would remember just as you're exploring the internet. It's the process of filling in these missing values. So when you say, hey, what'd you do with your missing data? I imputed it. Imputing it means you make up some other value to put in there. Now you make it up, but you usually make it up in a reasonable way. And so one way that you could say that, do that is we could say, hey, let's look at this entire data set and let's figure out what the average number of bedrooms is. Mean imputation. Let's say the average number of bedrooms is 3. And that's a really high average. So average number of bedrooms is 3. Maybe you look at your data and you plot your data and you find that you look at the distribution of your data. Remember when we talked about probability distributions, and you find that the distribution of your data is really skewed. And there are a lot of houses with like obnoxious numbers of bedrooms. So you decide that median is a better implementation. When in doubt and you're working on something on a scale like square footage, number of bedrooms, like price or salary, when in doubt, always use median. It's just going to be a better representation than mean. Mean is going to be heavily skewed by outliers. And of course, you could use mode if that makes sense. And there are scenarios that make sense. So imagine color is a great one. So we have color now of our house. Okay, so we have color of our house, and let's say this is a white house. There are a lot of white houses. This one's pink. And what's another color in the house? Gray. Boring colors. Okay. I wanted to use mode gray and name a house color.
Green.
Green. There we are. Okay. In this case, since it's a categorical variable like this, we probably just want to choose what occurs most often because there's going to be a bunch of different categories and we just want to choose the majority one. So in this case, we would impute with mode. This one, I would impute with median. This one, you could make an argument for mean. I think it would be fine. It might not be that skewed, but mean or median for a number of bedrooms. All right, so we're going to impute these, and now we've done the imputation and our data. We didn't delete this data, and this ended up being 2.5, which you can't have 2.5 bedrooms, but that's okay. And this ended up being 1,000, and then we had other values for these. So this was 5,000, and maybe this was also 300. Okay. There we are. There's our data set. That's imputation. Any questions on imputation?
In the real world, at time of inference, do you do the same thing if you're having to be missing those values?
You asked such a great question because I wanted to tell you guys this anyways, and now it's a good opportunity. There are a lot of people that set this process up wrong and incorrectly when they build this in their code. When you train your model, there are 2 stages to a pre-processing model called a fit and a transform. The fit method does things, it decides things, and it assigns, if you're familiar with object-oriented programming, it assigns values to the variables within the object. And so it decides things like, when you run fit, it decides what is the mean. So mean equals 2.5. That's determined when you run fit. Median equals 1,000. It takes all of the data, figures out the mean or the median. Mode equals white. When you do transform, what transform does is it applies those values to the missing ones. So it takes this saved variable and applies it. So when you have your training set, you'll do fit transform on your training set. The mistake people make, sometimes in production, they'll do fit transform on the data set they're predicting on. And that is wrong because you should be using the mean value from the model that you train, only your training set. And this is just saved and carried with your model into production. You should only do dot transform. You should only be filling in these values based on the average of your training set. So these averages are averages of your training set, and your test set, it knows nothing about your test or validation sets. Opinionated, actually that one's not opinionated. If you do it the other way, it's just wrong. That is a really good point though. I should underline that and put that in the data set. And let me pop over to code real quick, just for 1 second, because I think we're doing pretty good on time today, and I can show you guys. So when, I apologize, because this is the worst place to start, because this is like the end state code, and the best place to start is building it slowly, but we're just going to look at the end state code today. So Ignore all of this for just a moment while we talk about just something called Simple Imputer. So if you go to sklearn and you look up this thing called Simple Imputer, the Simple Imputer will impute those values for you. And you can define the strategy that you want to use for it. I'd encourage you guys to look that up on your laptop and really pull up that sklearn page and see that you can choose mean, median, and mode. It might say average, or I'm sorry, constant is probably the other one. You can also define a value. So you can define constant. So you can do mean, median, mode. I can create a brand new value called _missing. So sometimes if we're talking about house color and house color is actually missing for this one, that could be relevant in my data set. There might be a pattern of missing data that's relevant for a prediction. And I don't actually want to put a number there. I literally want to say missing. You can do that in sklearn. So you use the same Simple Imputer, you tell it that the strategy is constant, and you give it a value and you say missing. If you don't, in this one I didn't give it a value, it defaults with missing. So this step here, I even said in the comment, will impute missing values with the word missing. That would be, when you're working with like a categorical variable like color of a house, that would be my strongest recommendation because there could be some pattern there. You're giving your model some meaning. You're giving it more information about the data, telling it that that was missing data. Numeric features, you can't do that too, unfortunately, because this column has to all be treated of the same type. So since this is a 1 and this is a 2 and this is a 6, what you impute with has to be of that same type. So it has to be a number. We can't put the word missing here for number of bedrooms, or the model won't know what to do with that. What you could do is you could make a new column called is the bedroom missing, and you could do 0 or 1. And then that's how you can tell your model that bedroom was actually missing, and then you would continue to impute this with the median value. Throwing a lot at you guys today. So this is how you actually do that. And then I abstracted most of it here. I'll put together a little notebook that has that fit transform piece that I mentioned because I think it's important. Okay, I've any other questions on imputation before we move on to encoding? I've taken all my whiteboard space, so I'm going to erase and talk. All right, so we talked about what if we have a house we're trying to predict the price of, and we have a feature variable that's categorical. That means that it's not numerical. It's not on a scale, it's categorical. So it could be the color of the house. It could be a yes, no question, like does the house have Wi-Fi, yes or no? Maybe you're gonna go visit Alaska, needs a house with Wi-Fi. It could be, trying to think of other categorical variables for houses. If you're thinking about students, for example, and you're predicting if somebody is going to graduate or not, it could be, or not graduate or not. If you're working with a data set that has education in it, is what I was thinking of. I apologize. I'm not good at erasing and talking at the same time. If you're thinking about a data set that has a data set of customers and you have their education level, maybe you have high school education, has a undergraduate degree, has a master's degree, has a PhD. That's a categorical variable. So we need to do something with that. So the first thing we can do is we can encode it. So let's work with the color one in the house. So we have color. white, pink, gray, missing. I'm gonna put gray in here twice, so just we have some representation. Okay. More data, and of course there's more data this way. So here's our vector, here's our column vector, and we want to transform this so that we can put it into our formula of y equals beta sub naught plus beta sub 1, x sub 1 plus beta sub 2, x sub 2. We have 3 features here, plus beta sub 3, x sub 3, where this is 10 plus 11 times x sub 1 plus, I don't know, 12 times x sub 2 plus, this is what we're trying to determine. This one here, we're trying to determine color. How do we determine that weight? We can't multiply by these. One thing that you can do is encoding. So encoding is essentially taking all these values and just transforming them into numbers. You're creating a key. So now we have encoded color, and white is 0 because it's the first thing that we saw. Pink is 1, gray is 2, and missing is 3. Now we have an encoded thing. Now if we put a weight here, we can multiply it by 2. Say our weight is 2 now. Now we can say, as we input this into our model, 2 times 0, 2 times 1, 2 times 2, 2 times 3, 2 times 2. The problem with doing that for a variable like color is you are telling your model that there is something called ordinality here, that there is importance, a cascading level of importance. You're telling it that pink is worth twice as much as white, and that gray is worth twice as much as pink, and missing is worth 3 times as much as white, which is, or as much as pink and white. So it doesn't make sense. You're adding some ordinality to this. So this is called ordinal encoding. And it makes sense in some scenarios. So the education one that I talked about, if we have somebody that was a high school level, bachelor's, we have somebody in another high school, and then we have a PhD, and maybe we have master's. To this one, it might make more sense. Maybe high school's 1, bachelor is, high school's 1, bachelor's 2, master 3, PhD 4, there we are. To that might make sense. It doesn't exactly make sense. Is a high school, a bachelor worth twice as much as a high school? Well, I don't know, not really, but you can make an argument for ordinality here, that there's an order there and that it progresses naturally. So you want control over this. Don't let your machine just like apply the order without looking at it. Tell it what the order is. And you can do that in sklearn. You can look that up on Stack Overflow and such. You can define the order from ordinal encoding. So that's ordinal encoding. One-hot encoding. Okay, so what do we do with this? Well, we can do something called one-hot encoding, or OHE. And what OHE is, it sounds really fancy, but it's just really simple. We're going to create binary indicators for each of these variables. So in one-hot encoding, we're going to say, is it white? Yes or no. So what these end up being is they're called color underscore white. And then you'll have color underscore pink. You'll have color underscore gray. Okay, so we'll have, is it white? Yes, yes. No, 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 no. Is it pink? No, no, yes, no. No, no. Is it gray? No, no, yes. No, I'm sorry, no, 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 yes, no, yes. Okay. I did not make a color underscore missing. Does anybody know why?
absence of the column represents this.
Oh, that's interesting. You were close. I thought you were going the right way. I could have made not a column for gray, and I could have made a column for missing instead. So I made n-1 columns. Why?
Because you can determine it by everything by being 0, that it's that column.
Exactly.
It's implied.
It's implied. So when you implement this algorithm, just so you guys know, if you try to get the features back out of it, you will see n-1 based on how many labels there are. So how many labels? Labels equals 1, 2, 3, 4. There's 4 labels. You're gonna see calls equal to 3. Because it will always be n-1. You can determine if all of these are 0, it's obviously the other category. So you don't need to introduce unnecessary information to your machine learning model. It has all the information it needs in those 0s and 1s in order to determine that. That's a bit of an edge case thing, and it's not an edge case. It's a bit of a technical detail. You could really impress someone with that in an interview.
All right, devil's advocate here.
Yeah.
What if after this, so I'm doing all this, I'm gonna give it to the model, and the model doesn't need it. What if I want to know that when I'm doing reporting outside of the model?
Yeah, that's a real problem. You hit the nail on the head, because what often happens is we put all this information into the model, and we started with x sub 1, x sub 2, x sub 3, but maybe x sub 1 was states, and x sub 2, and there's 50 states, and x sub 2 is zip code, and there's thousands. And so we ended up with this 10,000 feature model, and when we look at the columns, they're just all like x1, 6, 8, 0, 2, 2, and there's just a bunch of zeros and ones. And there's 10,000 of those. And so it doesn't get useful from a reporting standpoint. So you have to translate those back, is my answer. And it used to be really difficult to do so, and I'm proud of a custom function that I built that actually did that. Now all such things are in sklearn, not all such things. It's a lot easier to do that now. I would say sklearn has built-in functions that if you use the packages in a well thought out way, like if you use that process and flow that I showed, you should be able to get these back in a very natural way. And it should be able to reverse apply. It remembers all the transformations it applied, and it can reverse apply those to get the information back out. That's what I would recommend.
I'm still playing devil's advocate.
Yeah,
So
I love
I know I'm not supposed to use them. I'm using a decision tree on its own. If I'm using a decision tree.
Good place to start. Good
Sure,
place to
yes,
start.
yeah, that's my base model.
Yeah.
Let's say. It will never get the node of color is missing to decide on. Right? Like I'll never have that as a decision point if that's not part of the thing. Like it's not its own column.
It can. So it's just by, it would be,
Color is not gray, not pink, not
Yes.
white,
yes,
which is 3 levels.
color is gray, no.
Right.
Color is white, no. And color is pink, no.
Fair, but from an understandability standpoint, it would be easier.
That's true. And I think if somebody look it up and correct me live here, I think you can make sklearn add the extra column.
I'm just.
No, I think it's a parameter in the function. When you look up one hot encoding, you can tell it, which I have done before for exactly what you're talking about. Like I just want that column back out. So when I build a dashboard and my stakeholders look at it, it has all the values and they're not confused because that doesn't resonate with them. So yes, you can force it to add that other column.
Right.
And I would agree with your argument that if you're building a decision tree and that's a very important feature, the one that gets dropped off on the end, that it's not going to show up in your feature importance at the end of the day because it's not a feature. So I would argue adding it to a decision tree.
And you could get into a problem if you're only going to a certain depth, right, that it never gets there. 'Cause then
Correct.
you go, no,
Correct.
no, before it got to the thing.
And yet, and if you're looking, like at the end, you'll get this thing called feature importance, and it'll have white on here and pink and gray, and it won't have missing. Missing won't be on your feature importance chart. And when in reality, if you did have missing, maybe it was like very important, you know, so it just wouldn't be on your chart because it wasn't a feature. Yeah, so I agree with you. You should continue to ask questions like that. This is the point of the class. If you guys just wanted someone to talk at you, you could just watch YouTube videos. Yes, all these things, very important. One hot encoding drops a column by default. You can, I'm 90% sure you can change that in the program. Somebody can correct me if I'm wrong.
It looks like retain all features, so the parameter drop, and
Yeah.
it does default to not drop it.
Oh, it defaults to not dropping it. I stand corrected. By default, I guess it doesn't drop that. That actually makes a lot of sense. But you can make it drop it. Okay, that's helpful. All right, so how does everybody feel about encoding and one-hot encoding? And this type of encoding is ordinal encoding, whereas encoding that wouldn't be ordinal is if it was just a binary variable, yes, no, 1, 0. That's just ordinal encoding, or that's just encoding, not ordinal. Okay, because right now we're going to talk about scaling. I don't think I need to whiteboard anything for this one. I think this will resonate with you guys. So we looked at some models and algorithms such as the clustering one, k-means clustering. When we looked at k-means clustering, we said that was really susceptible to scale. So if we gave it houses, and if you look at square footage in a house, then if you take the max value and the min value and you subtract them, it's a really big number. So that means there's a lot of variation there, and that variation that you see in that number is very different from the variation that you see in number of bedrooms. If you take max number of bedrooms minus min number of bedrooms, you compare them, the variation between those two are very different. And so there would be problems if you tried to use k-means clustering. So what you should do is you should scale. So you should apply some type of normalization technique to bring those values down to the same order, the same level. Now, it doesn't change, just like all the other things that we've talked about, it does not change the order. So if there was a house that had more square footage than a different house, the house with the smaller square footage will never move up in the data set and somehow have more square footage than the house with bigger square footage. The order remains the same. We're just shrinking all of those values down to reasonable domain. There's many methods that you can use to scale. There are two that are relevant or popular, I guess is a better word. There are two very popular ones. There's min-max scaling, and there is standard scaling. And the difference really between the two of these, which I have the formula up there. I'm questioning the correctness of this. One moment. This is not matching with. Oh, where's my mouse? Sorry, I gotta figure out how to get this back on. Okay. No, okay. Seems Correct. If I have a correction after, I will share with you guys. For now, I'll continue. So min-max scaling scales between 0 and 1. And the way that that is done is, remember I was talking about the max value of the column, the minimum value of the column. That's what this one uses to scale. So we take the max value of the house, the max value of square footage. When we're talking about X here, we're talking about a specific column. We're scaling a column. This is applied to every column. The max value of square footage that exists in your data set, maybe it's like 1 million. The minimum value of square footage, maybe it's like 150. You subtract those two values, and then you take your value minus the minimum, and for every value in that data set, and then divide that by that value that we just calculated, and that will rescale your data to a fixed range, typically between 0 and 1. The other one is standard scaling. So this one's going to use the mean and the standard deviation. So we're going to take the average value of the column. We're going to take your value, for each record. We're going to take that record minus the average value for the column and divide by the standard deviation. And this will cause it to range between, it'll have a mean of 0 and a deviation of 1. So on average, the value will be 0 and it'll deviate to 1. Okay.
There are benefits of one over the other.
You know,
Pick your favorite.
there was something that I was going to say, but I don't want to misspeak. So I have to follow up on something on this slide real quick. And then if I send a correction afterwards, I'll share that with you guys. But the thing that I was going to speak to is that there are times when you don't want to scale to be below 0. There are some algorithms that you may implement where this one will handle negative values just fine. You can multiply by a negative value and that's fine. There are some implementations or some reasons why you might not ever want a negative value. So there are some scaling algorithms that you can apply that scales between 0 and 1. So that's the only edge case that I've reached, is where I had an algorithm I was using that didn't take a negative value. And so I had to scale everything, didn't make sense. So I had to scale everything to be between 0 and 1 for it to make more sense, as opposed to -1. Yes, I believe that was. So this one goes between 0 and 1. I believe this one goes between -1 and 1. So yes, I think that's the situation that's the specific situation I was talking about. I think I was just reading this slide incorrectly. I think it is correct. So this one is not negative, is what I'm saying, typically. Okay, if your data is positive. So like number of bedrooms is positive, but there's no negative values that exist in that. So when we scale that, it should be a positive between 0 and 1. Whereas this one will have a mean of 0 and a deviation of 1, so you have negative values.
Would you have a reason to use both at the same time?
Sure, yeah, you can use different scaling methods on different columns.
Okay.
So to one column, you have to choose. You either min-max scale it or you apply standardization, but you absolutely can apply different standardization techniques to different columns. Now you're going to violate some of the problems, the whole reason that we chose to apply these in the first place, if you choose ones that don't have the same range. So if one goes from -1 to 0 and the other goes to 0 to 1, you're still going to have that same problem with clustering, k-means clustering, where it's going to bias towards the one with the bigger range, for example. That's a good question. Any other questions on scaling? Okay. Feature engineering versus pre-processing. I just want to clear something up and offer like an opinionated perspective. This is all about opinions today. Feature, oftentimes people call those steps that we just talked about, imputation, scaling, one-hot encoding, what else? I think those are what we talked about. Oftentimes people will call that feature engineering. Some people will call that feature engineering. I do not call that feature engineering. I call that data pre-processing. You're not really changing the nature of the data. It still represents the same thing that it is today. You're just organizing it and restructuring it. You're transforming it in a way that so that it's ready for input into the model. Now, feature engineering means you're deriving, this is, I guess, again, opinionated perspective, but just so you guys know, when you explore the internet, you will see these things kind of mixed up. A lot of people say, when they're talking about one-hot encoding and such, will say feature engineering. I prefer feature engineering to be applied to creating something of new value. So some new information based off of other information. I'll give you an example. If you have a date, you cannot put a date into a machine learning model. We might engineer that date to represent day, month, year as separate column vectors or represent it in some other meaningful way. There are some models that can take dates, but generally speaking, if we have, what's the date today? October 2nd, 2024, we'd have to break that down into the day, October, that the number associated with the day, the month, and the year, and then apply these same techniques, encoding, one-hot encoding, or some other creative approach in order to get value out of that. Or maybe, here's a better example. We have age, and we just transform it into, or we have birthday, for example, we just transform it into age. That would be kind of engineering that feature. It's a very simple one. You can make very complicated feature engineering. You can derive value from that one column or a combination of columns in order to create a new feature for input into your modeling. That's what I consider feature engineering and pre-processing.
How do you determine if the new feature you created had a negative impact on your model? Because you don't necessarily know what's going to help it.
That's such a great question. So there is an approach called feature selection. Is an entire domain. I should have put a slide on it, but I do not. And there are, but I have a notebook. Feature selection, oftentimes one problem that we face in machine learning is sometimes we have too many features. Or to your point, we have some features and we want to know if we add a new one, is it valuable or not? And so sometimes we want to select the right set of features because we know there's a lot of noise and we know we could use everything, but we just want to use the most informative things. So feature selection is a process that chooses which features to include based on performance, basically. Basically, what you do is you add a feature, you measure the performance, you take the feature away, you measure the performance, and you see if it was better or worse. Now, they have more sophisticated methods for this, for feature selection. Hold on, let me get down to them. So feed forward is the one that I talked about where you start with like 2 features, then you add a 3rd feature and measure the performance. You guys did this. You built your own feed forward process in your linear regression. You did feed forwards feature selection. You at least put the performance metrics in there. So you had a performance and then you added a feature and you saw, did it increase or decrease? And then you added, and if it would have decreased, in reality, you would have dropped that out. Then you would have added a new feature, then it would have increased or decreased. And you can imagine some of the challenges with doing that. You can imagine like, well, you're not doing a linear combination. So how do I know that the combination of that feature you dropped off and some other feature wouldn't have actually been informative? And the truth is you don't. That's the problem with feed forward selection is when you throw out a feature, it's thrown out forever, regardless of any combination of other features that it hadn't yet been compared with. So here's an example. You have your null model, and then your model with one variable, you measure that. If it's good, you keep it. You grab another marble out of the jar, another variable, you add that, you keep it. You can, of course, go the other direction. So you can go backwards. You can put all the marbles in, all your features in, and then you can figure out which you calculate your least significant variable. So in random forest, I told you can get feature importance. What's the one with the smallest feature importance? Take it out. And then start to remove these until you meet some acceptable threshold. And then there's more sophisticated methods like recursive feature elimination. So people, of course, those are the like simple ones, forward and backward. People, of course, have created more robust techniques. And I think I even have some examples here. So did that answer your question?
Yeah.
Okay, good.
When you're doing those changing out, so we did it poorly because we did it on the test one. We normally do that against your validation sets.
Is feature section one like a training set?
Training set, I would recommend.
Okay.
Validation is for different types of models. And then the test is the final, only once.
But how would
Only
you
once.
know-
Don't do it on your test
But
set.
how would you know how you perform unless you test it against something as part of the feature?
Cross-validation.
Okay, got it. Okay.
K-fold cross-validation.
Which
For
is
feature
essentially
selection.
doing like a little mini test.
Yep, little mini test set. Yeah. You're taking your training set and making mini test sets. You don't want to overuse your validation set or you'll hit that same problem where you're going to think you'll trick yourself. You think you're going to have good performance and then what will happen is you're really tuning your model to your validation set. So I try to only use it when I'm kind of at a big decision point where I've got several different implementations or processes, and I want to choose the best one.
Run well on the cross-validation.
Yeah, they've all done their own individual cross-validation and hyperparameter selection and feature elimination. If you're running this more than if you're using, I'm trying to give you a thumb in the air thing, but I'm afraid it's going to be too hard of a rural. I was going to say, if you're running iteratively on your validation set, like more than 10, 15 times, it's probably too much. That's such an arbitrary number. So also take that with a grain of salt. It really depends on what you're doing. Okay, we have 4 minutes. So we will not talk about K nearest neighbors. There's a modeling methodology notebook here that has some generalizability stuff, train, test split, data pipelines. There's some examples in here, and you guys here's a stratification example that does train, test split with stratification. Oh, this one does train, test split with stratification. So stratify equals Y is the parameter that you pass to train, test, split. There's some other, similar concepts to everything that we've talked about today in these notebooks. There's pre-processing. Oh, I should have showed you guys this one for the encoding example. So we have red, green, blue, red when you apply something called a label encoder. And remember we said fit transform. Here's that fit transform method on the label encoder that then turns this into 2, 1, 0, 1, 2. So when you call just fit, you can call label encoder.fit and pass color. And if you do that, it determines the mapping. It says red is 2, green is 1, blue is 0. When you call transform, it applies that mapping. So when you're applying things to your data set, you only want to pi trans. Oh, I know what I want to go over. The last 2 minutes. 2 minutes here. This is what I wanted to get to by the end of this whole thing. Let's build a pipeline together. The first thing we're going to do is, actually, it's a little easier if we start at the bottom here, so please forgive me. We're gonna start with our fit method. What we want to do is we want to fit a model. We want to call sklearn.fit, and we want to pass it our x data and our y data. This is just transforming the y data. Don't worry about the np.ravel. You can take that out. So we want to call .fit on our xy. And we want to call that on our model, which in this case, we're going to train a random forest classifier. But we don't just want to train one classifier. We want to run a grid search over many parameters. And so we're going to use this thing called grid search CV, grid search cross-validation. And we're going to give to this sklearn function, this is an sklearn package, an estimator. And our estimator in this case is a pipeline, which we'll get to in a moment. But one of the steps that it contains is a random forest classifier. We're going to give it a parameter grid. So this is a dictionary or a list, in this case, a list of a dictionary that has the mapping of, for a random forest, I want you to search n estimators, 50 and 100. For random forest, I want you to search max depth. For random forest, I want you to search min leaf. The reason it's set up like this is because you could theoretically actually put other models in there. You could put logistic regression, that stuff. But let's start with one. Then you're going to tell it how you want it to score. You have to give it one method, one metric, one objective function. How is it going to do better? In our case, we gave it F1. You don't have to know what that is. We talk about that in the next class. And then we told it we want it to do 5-fold, CV equals 5. So it's going to split into 5. You don't have to worry about these other things here. We can talk about those another time. So this is the min you need here. It's just the estimator, the parameters you want it to search over, F1, CV is 5. Fun fact, CV is 5. We have 1, 2, 3, 4, 5, 6 parameters here. Does anybody know how many models this will train? Yeah, nice. How'd you get that?
The two estimators there times the free max depth, then there's the one, which is just one, and then multiply by 5 folds.
That's exactly correct. So even though we don't have like a lot of parameters, we're searching over here, 2 times 3 times 1 times 5, we actually end up training 30 models. So this still might take a minute to run. Okay, so we know how to do CV now. Let's figure out what this estimator RF pipeline is. So moving up just a little higher. I know we're at time. It's okay if you guys have to drop off who are on the call here. This will just take 1 more minute, I promise. RF pipeline is something that we defined, and we're using this function in sklearn called a pipeline. And what's great about pipelines is you can tell it do step 1, then do step 2, then do step 3. And so we're telling it, hey, do step 1, and I want you to pre-process the data. We'll talk about that in a minute. And step 2, only after the data is pre-processed, I want you to then apply this random forest classifier. And so this is our RF pipeline that we pass to our estimator. The power of doing it this way is that at the end of this, we don't just have a random forest model. We actually have, when you call best estimator here, we actually have a grid search object that has the best model that includes all of the pre-processing steps. So when you call predict on this model, all you have to do is you pass me your data in the original state before these transformations. I will transform them. I'll do the one-hot encoding. I'll do all of this for you, and then I'll make a prediction. So you can give me plain vanilla data, And within one object, one model call, I can make predict on that data. It used to be, the reason this is really cool and why I think it's so great, because it used to be you had to do like this preprocessor and you'd have this preprocessor object, and then you would have this random forest, this model object, and people messed up the steps all the time and it was really gross. And this fixed it. So 10 out of 10 would recommend this sklearn pipeline.py process. I'll share this with you guys. It's just so much cleaner. You only have one object you work with. And in an instance where you need to retrain the model, some people have retrained the model, not retrained their data preprocessor, and then you get errors between them. It's just less problems to introduce. Okay, so what is a preprocessor? When we want to do preprocessing, you may want to apply transformations to different variables. So, and maybe I'll dive more into this next time because we're getting a little far past time now, but on a really short note, in a simplistic way, you can break this down into numeric and categorical variables. In our house, bedroom's numeric, square foot's numeric, and color's categorical. So the transformations we want to apply to our categorical variables are different than our numeric variables. This gets to your question. If you wanted to scale things differently, you would have to define them as different transformers within this. Okay, so what's a numeric transformer? In this numeric transformer, we're again using this really cool pipeline thing, and we're defining 2 steps. We're saying first you need to impute with the median, and then you need to min-max scale. So anything that is numeric, our bedrooms, our square footage, will impute with medians, and then they will scale. Anything that is categorical, on the other hand, we're going to impute with that missing constant, and then you can ignore this for a second. Sorry, that's unimportant. That's just confusing. For now, we're going to impute with this missing constant, and then we are going to ordinal encode them. So all of them will be ordinally encoded variables. So it's going to apply that transformation to our numeric and our categorical, and then it's going to apply both those steps, and then it's going to fit predict on the random forest classifier. Fit, of course, if you are in this training state. Of course, when we use this best estimator object, it will just be predict. I'll put this back in because that'll be useful for you guys later, but okay. That's it. Thank you guys. I'm going to end the recording now, and we can talk more on that next time.